Welcome back everyone. So, in the last lecture, we have seen how to find the inverse Laplace transform using partial fractions. Now, in this lecture, we will see what is convolution theorem for Laplace transform and how to make use of convolution theorem in finding the inverse Laplace transforms. So, according to the convolution theorem of Laplace transform, if the Laplace transform of f1t is capital F1s and the Laplace transform of f2t is capital F2s, then the Laplace transform of convolution of two functions f1t and f2t is equal to the multiplication of their Laplace transforms, or inversely Laplace inverse of multiplication of capital F1s and f2s is equal to the convolution of f1t and f2t. Now here, to prove this, you must have the knowledge of concept of convolution. I mean, this is a prerequisite for this lecture. If you want to know what is convolution or want to refresh your concept of convolution, I suggest to go through the video lecture on concept of convolution. I have mentioned the link of video lecture below. Okay, so let us see how we can prove this. So, by the definition of convolution, we can write Laplace transform of convolution f1t and f2t is equal to Laplace transform of integral 0 to t f1 tau into f2 t minus tau d tau, which we can also write it as integral 0 to infinity e raised to the power minus st into integral 0 to t f1 tau into f2 t minus tau d tau into dt by the definition of Laplace transform. Now, by taking e raised to the power minus st inside the integral, it becomes integral 0 to infinity into integral 0 to t e raised to the power minus st into f1 tau into f2 t minus tau d tau into dt. Now, we are having a double integral equation. Okay, so to prove the theorem, we need to change the order of integration, and for that we need to find the new limits as well. So, let us find the new limits. For that, let us first represent our original limits by taking tau on x-axis and t on y-axis, and draw the area which is represented by the limits. Now here, tau is varying from tau equal to 0 to tau equal to t. These are the limits for d tau. So, what is tau equal to 0? It is t-axis line, this one, and tau equal to t is a straight line as this one. Similarly, what are the limits for dt? T equal to 0 to t equal to infinity. So, t equal to 0 is the tau axis line, this one, and t equal to infinity means entire this region. So, the area bounded by both these limits will be this one. Now, to change the order of integration, we will assume a strip parallel to tau axis as our first integral is with respect to d tau. Now, let us check whether strip is following the limits. In horizontal axis, strip is varying from tau equal to 0 to tau equal to t. And in vertical axis, strip is varying from t equal to 0 to t equal to infinity. Now, to change the order of integration, let us take a strip parallel to t-axis. So, what are the limits for this strip? T is varying from t equal to tau to t equal to infinity. And tau is varying from tau equal to 0 to tau equal to infinity. So, by changing the order of integration, we can write the above equation as integral 0 to infinity into integral tau to infinity e raised to the power minus st into f1 tau into f2 t minus tau dt into d tau. See, here for dt, these are the limits t equal to tau to t equal to infinity. And for d tau, tau equal to 0 to tau equal to infinity. Now, we can also write this as integral 0 to infinity e raised to the power minus s tau into f1 tau d tau into integral tau to infinity e raised to the power minus s into t minus tau into f2 t minus tau dt. Just by multiplying first term by e raised to the power minus s tau and second term by e raised to the power plus s tau. Now, let us consider t minus tau equal to u in second integral. So, dt equal to du. And the new limits for u will be when we put t equal to tau, u equal to 0. And for t equal to infinity, u equal to infinity. So, we get the equation as integral 0 to infinity e raised to the power minus s tau into f1 tau d tau into integral 0 to infinity e raised to the power minus su into f2u du. So, now we have the terms in the form of Laplace transform of two functions. So, by changing the variables tau and u by s. We can write it as f1s into f2s. Thus, it is proved that Laplace transform of convolution of f1t and f2t is equal to multiplication of Laplace transform of f1s and f2s. Or inversely, we can also say Laplace inverse of f1s into f2s is equal to convolution of f1t and f2t. Now, let us see how we can use this property or this theorem in finding the inverse Laplace transforms. Example 1. Using convolution theorem, find the inverse Laplace transform of s by s square plus 1 whole square. Let's see how we can find this. As we know that Laplace inverse of s by s square plus 1 is cos t, and Laplace inverse of 1 by s square plus 1 is sin t. So, by using convolution theorem of Laplace transform, we can write Laplace inverse of s by s square plus 1 into 1 by s square plus 1 equal to convolution of cos t into sin t. That is, Laplace inverse of s by s square plus 1 whole square is equal to convolution of cos t and sin t. Now, we can find the convolution of cos t and sin t by the basic convolution theorem. So, we can write convolution of cos t and sin t equal to integral 0 to t cos tau into sin t minus tau d tau. Now, this term cos tau into sin t minus tau, we can write it as sin t by 2 plus sin t minus 2 tau by 2 by using this trigonometric identity. Now, we can evaluate the integral easily. So, on solving the integral and putting the limits, we get the convolution of cos t and sin t as 1 by 2 into t into sin t. So, we got the inverse Laplace transform of s by s square plus 1 whole square as 1 by 2 into t sin t. Let us take one more example. Using convolution theorem, find the inverse Laplace transform of 1 by s into s square plus a square. Solution. We know that Laplace inverse of 1 by s is 1 and Laplace inverse of 1 by s square plus a square is equal to sin at by a. So, by using convolution property of Laplace transform, we can write Laplace inverse of 1 by s into 1 by s square plus a square equal to convolution of 1 and sin 80 by a. So, we need to find the convolution of 1 and sin 80. So, by basic convolution theorem, we can write the convolution of 1 and sin 80 as integral 0 to t sin a into t minus tau by a into d tau. See here that the first function, that is 1, does not have t variable. So, the integration does not have function of tau. Now, by solving this integral, we get the convolution of 1 and sin 80 as 1 by a square into 1 minus cos 80, which is the Laplace inverse of 1 by s into s square plus a square. So, in this way, we can also make use of convolution in finding the inverse Laplace transform.